Welcome to today's online class. We are going to continue with the section that we left last time. And in discussion, just to recap, we said that the stress and the strain, they are the two major items that we are supposed to discuss in this unit. And also we said that when we are looking at the stress, it is given by force per unit cross-sectional areas. And when we are looking at the strain, it is the ratio of change in length to the original length of that material. We also said that when you have the stress and the strain, the naming is dependent on the type of the force that is pushing that material or pulling that material. And therefore, when we have this kind of items, we need to know that the stress and the strain, they are the one responsible of causing the deformation in any material. So today I want us to look at the composite material. And when we are looking at the composite material, this is material that is made up of two or more different types of materials. And the purpose of this one is to increase the stiffness or the strength of that material. When we have an engineering beam or I-beam, as you can see from that diagram, it is made of two different materials in the sense that the fridges are made of wood, plywood, and that is the web is made of plywood, and also the fridges are made of solid wood material. The one that you can see here, the second diagram, involves the double pipe beam, and the interior, as you can see, because of different coloring, they are made, the interior and the exterior are made of two different materials. But because they act as one component, it is called a composite materials. In the compound material, one thing that you need to know is that the stress is different. That is, material 1 and material 2, they have two different stresses. But then, when we come to the strain, they are the same. The strain is the same in case of a compound material, while the stress is different. But then we need to know that when we are calculating the Young modulus, the Young modulus will always be given by the ratio of the stress over the strain. And therefore, because the stress and the strain, that the strain of the two materials are the same, then it means that E1 and E2, they are the same. That the stress of the first material and the stress of the second material, they are the same. Then if we equip the two and calculate the load, the equations, as you can see from the second one, the P is equals to A1, you multiply by force 1 plus A2 times force 2. The resultant stresses are going to be as given in this equation. That is, the stress due to number 1, the first material, is going to be given by the equation, the first equation, and then the stress because of the second material is going to be given by the second equation. So P is the force in that case. A1 is the area of the first material. A2 is the area of the second material. E1 is the Young modulus of the first material, and E2 is the Young modulus of the second material. This is how you can be able to determine the resultant stresses in the two materials. So that is as far as topic number 1 is concerned. Looking at topic number 2, we are going to see that we are going to have the structural beam. When we look at the structural beam, one thing that we need to know there is that these are the structural members that support the loading applied axially or perpendicularly to their longitudinal axis. And we are going to see that when there is, that is, they are going to withstand the load, the shear force, and the bending moment, and transfer all the imposed load to the end points, which can either be a wall, a column, or a foundation. And in this case, we are going to classify the beams in two main ways. One of them is we can classify the beams depending on the manner in which they are supported, either simply supported beam, fixed beam, overhanging beam, or a cantilever beam. We are also going to classify the beam depending on the profile or the shape of their cross section. That is, we can talk about rectangular, we can talk about circular beam or trapezoidal beam. We can also classify the beam depending on the length. That is the short beam and the long beam. We can also classify the beam depending on the manner in which that is the material in which they are constructed, like the wooden beam, the plastic beam, and the concrete beam. So these are the four main ways upon which we can be able to classify any beam. But in our discussion, we are only supposed to concentrate on the classification of the beam depending on the manner in which they are supported. For example, we are going to look at 2 or 3 examples of this. So classification of the beam depending on the way they are supported. One of them is called a simply supported beam. As you can see from this diagram, a simply supported beam is a type of the beam which is fixed at one end, as you can see, and the other end is left on top of a rollers. So the maximum bending moment is going to occur at the midspan, and we are going to have the shearing force occurring at, that is the maximum shearing force occurring at the end points of the support. So if you have this kind of a beam, it is called a simply supported beam. This kind of a beam is known as a simply supported beam. It is supported at its edges, and then you have the maximum bending moment occurring at the center and shear force maximum occurring at the point of support. Then we have continuous supported beam. This continuous supported beam, it resembles a simply supported beam, as it the only difference is that it has many supports. One end is fixed, as you can see from the first one, and then the other supports are left on the roller, all are on top of the roller. This kind of a beam that has multiple supports and resemble a simply supported beam is known as continuous supported beam. Then we have another type of beam that is called cantilever supported beam. When we are looking at the cantilever supported beam, one thing that we need to know is that only one end support at one end. Only one fixed end is supported at, that is support the beam. And then the other end, as you can see, is left hanging. So only the left hand side in this case of a beam is fixed. The rest of the section is left hanging. It carries a load over the span, which undergoes both shear stress and the bending moments. So this is the kind of the beam that I am talking about. Then I have another kind of a beam that is called overhanging support beam. This is a combination of cantilever beam and also a simply supported beam, as you can see. One end is fixed, the other one is left on rollers, and then we have the furthermost end, as you can see, the left hand end is part of it is hanging. So this is the reason as to why it is called hanging beam, overhanging beam. So it inhabits both the properties of simply supported beam and also the cantilever beam. Then we have another kind of a beam that is called a fixed support beam. This beam is fixed on both ends, and it does not allow any movement either horizontally or vertically. The only thing that is experienced here is the shear stress, and that there is no movement that can be observed. And this kind of support is in most cases used in trusses and other structures. So this is the kind of a beam that I'm talking about. Both ends, the left and right hand side, is fixed, and also we have the beam producing the shear stress. The shear stress is the only thing that can be experienced there. Then we have double overhanging beam. It is a simple beam with both ends extending beyond its support. As you can see from the left hand side and the right hand side, there is a section that is still hanging, and the support are interior or inside the support. So this kind of beam, whereby two edges are hanging, is called double overhanging beam. Then we are supposed to look at the type of the loading system. The type of the loading system, we have two main types of the loading system. We have the concentric load That is the single force. In this case, the force applied acts only at a single point. The force that is applied, it acts only at a single point, and it is called a point load. That is, it is called a point load. So when we have concentrated load, when we have concentrated load or single load, the force that is being applied, as you can see from this diagram, the force P is only applied at one position, and it is called a single point, single load, or it is called a point loading. The load applied at the center produces maximum deflection at that point. Therefore, it means that I have the simply supported beam AB. As you can see, it's a simply supported beam, and there is a force P that is acting at the center D of that beam. Then we have at the left and the right, we have L/2, meaning that the force is at the center. This kind of loading is the one that is called a point load or a single load. Then I have this other type of loading. This is a simply supported beam AB. It is a length L, and it is applied, that is W Newton per millimeter squared. So the weight is uniformly distributed. This is called a uniform distributed load, since the weight is being distributed from number A to number B. Then there is a force applied act uniformly along the entire beam. So this kind of loading that is not acting at one point, but it's acting at the entire length of the beam is the one that is termed as the uniform distributed load. There is something else that is called the support reactions. When we are looking at the support reactions, there is something that I want us to know. That's loading of the beam, either the point load or a uniform distributed load. There is a force of action that is being applied. This force of action, because of the loading, it will produce the reaction force at the support, meaning that P is the action force. A and B, it is going to counteract the force of action, which is P. And therefore, the reaction force is the one that is going to be produced. So force P is action force that is being imposed. Then at A and B, the reaction force is produced whose sum is equal and opposite to the reaction force. So we have A, support A, and support B. They are going to produce the reaction force when we have the action force of P. Then there is something that is called the moment at the support. Moment, we know that it is given by force you multiply by a perpendicular distance from the point of the support. And therefore, if I want to know the moment at A, it is going to be given by L/2, which is the distance from A to D. You multiply by force P. So L/2 times P is the one that is going to give me the moment at point A. So force times perpendicular distance. There are three main conditions that we must fulfill for any stable or equilibrium beam. One of them, for a beam to be equilibrium or stable, the upward force must be equal to the downward force. The horizontal forces must be equal to 0. And the summation of the clockwise movement about any point should be equal to the sum of the anti-clockwise movement about the same point. We are going to look at this in detail. We are going to look at this in detail when we are doing the calculation. So I'm just going to give you an example of how you can be able to calculate a reaction at the support. We have been told by this equation that calculate the reaction at the support R1 and R2 of a simply supported beam shown in the figure. We have a simply supported beam AD, and then we have at A and at D, we have a beam that is supported, that is the support of the beam. C and D, we have 100 kilogram and 400 kilogram weight that is applied there respectively. The distance between R1 and R2 is 6 meters. And then you have the information as you can see from that diagram. So what is the solution? What are we supposed to do? The first thing that we need to do is to take the moment about one point, say point D, for example. We are taking the moment from point D. Moment is force times perpendicular distance from the point of support. And therefore, if I want to know if the moment of B from D, it is 1,000 kilogram, you multiply by 10 to make them Newton. Then I multiply by 3. 3 is the distance from B to D. 3 is the distance from B to D. Then I should add to the other moment, which is 400 kilonewton. You multiply by 10 to make them Newton. Then I multiply by 1.5, the distance from C to D. Those are going to produce the clockwise moments. Then I am supposed also to say that clockwise moment is equal to the anti-clockwise moment, whereby the only thing that is making our beam to go in the anti-clockwise moment is A. So the action at A, I multiply by 6 meters. 6 meters is the distance from D to A. That will give me the anti-clockwise moment. Then I add the 2. That is, the clockwise moment should be equals to the anti-clockwise moment. So R1 times 6 is that one of A, that is 6, the distance from A to D. I multiply by R1. It should be equals to 400 times 1.5 plus 1,000 times 3, so that I can get in kilogram R1 to be 600 kilonewton. Then the same case is going to apply to the second point. The second point is R1 plus R2, which is the upward force, should be equals to, that is R1 and R2. As you can see, R1 and R2, the reaction force is equals to 400 plus the 1,000. And therefore, R1, we have said that it is 600. And therefore, I just replace to get R2 to be 800. Thank you. We can continue from